Okay, so in the previous video when we looked at factorization of polynomials, I mentioned that the first step was to take out any common factors. The second step was then to use either the factor theorem or the rational root theorem to identify one factor. So we hadn't talked about the rational root theorem to that point, and so we're going to do that now. So one of the problems with the factor theorem is that it relies on there being a factor of the form x minus k, where k is an integer. Otherwise, you have infinitely many possibilities to test. So the problem is sometimes a perfectly normal looking cubic function might not have any factors of this form. So if you have a look at this cubic here, when we factorize that, when you look at that in factorized form, it has three linear factors. But one is 3x minus 1, so that would require us to sub in x equals a third to discover that 3x minus 1 is a factor. And as I said, factor theorem, yes, you could technically use fractions, but you open up a whole wide world of possibility. And the other issue is that the other two linear factors involve surds. So there's even more possibilities if you allow yourself to go into the realm of surds. And so using the factor theorem, we wouldn't find a linear factor here. We would look at this 5 and we would say, okay, I'm going to try p of 1, I'm going to try p of negative 1, I'm going to try p of 5, and I'm going to try p of negative 5. And none of those would give you 0, and then you'd be stuck. So at that point, then we need to go to the rational root theorem. So what the rational root theorem says is we look for that rational factor, so this one. The one that's going to give x equals a third as a solution, so a rational answer or a rational root. And so if we can't find an integer that makes this true, which is what we just did, then we assume that there's going to be a factor of this form. We assume there's going to be a factor that results in a rational root, that is a fractional root. Okay, so if we say, okay, well this polynomial is going to have a factor of this form and then there'll be other factors, okay, then we know that if that's a factor, p of negative b over a will have to equal 0. Now, the other thing to think about again is that the trial and error that we need to do is not infinite, okay? So if this polynomial equals this when it's factorized, who knows what the other factors are, but if one of the factors is x plus b, we do know that a has to be a factor of 3, okay? And we also know that b has to be a factor of 5, okay? And we want to test options of the form negative b over a. Okay, we can just test b over a, we can interpret our answer once we get it. So what that means is, all right, we now know from this information here that a is going to have to be plus or minus 1 or plus or minus 3, okay? And we know from this information here that b has to be plus or minus 1 or plus or minus 5. And so if we then think about what that means for b over a, or negative b over a, we'll worry about that later, we could have plus or minus 1 over plus or minus 1. We could have plus or minus 1 over plus or minus. So we don't have to worry about the plus or minus on both the top and the bottom. So therefore we could have plus or minus 1 over 1, which we've already tested theoretically, plus or minus 1 over 3. We could then have plus or minus 5 over 1 and plus or minus 5 over 3. Now, we assume that we've already attempted to use the factor theorem and discovered that there are no whole numbers that go that give a remainder of 0, hence there's no factors of the form x minus an integer, and so therefore we've already tested positive and negative 1, and we've already tested positive and negative 5. And so there's 4 fractional possibilities that we need to test, okay? There's no shortcut around this. You sub them in until you find the one that gives you 0, and you hope that it's one of the early ones that you try. Okay, so here, for example, we look at trying positive a third first. We sub in positive a third. That does happen to give us 0, and so therefore, if p of a third is equal to 0, that means that 3x minus 1 is a factor. And then once we've used our rational root theorem to identify that one factor, we can divide to find the other factor. We discover that it's x squared minus 5, which we could factorise to x minus root 5x minus root 5 if it was specific that we needed to give linear factors, because this is a quadratic factor. However, if the question is just to fully factorise, we actually don't need to go this far. If we have to go to the territory of surds, we're going above and beyond. Even if you have a look at getting your CAS to factorise this, so if you have a look at menu 3.2, factor, and get it to factor, 3x cubed minus x squared, minus x squared minus 15x and plus 5. If you just press enter there, it is going to give you 3x minus 1 times x squared minus 5. So it's not going to go into the realm of surds unless you force it to. The way to force it when you do the factorisation is to put comma x in the factor bracket, and then that will force it to factor it over both the rational and irrational numbers. But in terms of fully factorised, 3x minus 1 times x squared minus 5. If the question was, expressed as a product of 3 linear factors, well, this is not linear, and so therefore we would need to go to this point. That's just a difference of 2 squares. X squared minus root 5 squared is x minus root 5x plus root 5. Okay, but the key idea is we're looking for, alright, if our whole number factors fail us, so if we try, as we said, p of plus and minus 1 and we don't get 0, and we try p of plus and minus 5 and we don't get 0, they're the only options that are going to give us 5 at the end here. We then need to assume there's a factor of the form ax plus b. Think about what we know for the possible values of a and the possible values of b. Think about what that means for the possible fractions b over a that we need to consider, and then start substituting fractions in until you find something that gives you 0. You do need to do the fraction work by hand. Okay, I know it's tedious, but if you had a CAS, you wouldn't be doing any of this. You would have just hit factorise. So if you're going to need to do this, you're going to need to do it by hand. Realistically, to be honest, it's unlikely that you're going to be assessed on this in an exam. It is in the course in both Units 1 and 2 and in Units 3 and 4. I teach it again at Units 3 and 4 as well. But really, it's really hard to put it in an exam, because if you get unlucky and the 4th fraction that you test is the right one, you've spent 4 times as long as anyone else on this single question, and it's not a small amount of time. And we haven't really tested a huge amount beyond getting you to just work through a whole lot of fractions. Okay, let's have a look at a couple of examples. Alright, so we're going to factorise 4x cubed plus x squared minus 12x minus 3. Now there's nothing in the question that suggests we're going to need rational root theorem. We certainly wouldn't jump to that straight away. So my negative 3 tells me that I'm going to test positive and negative 1, positive and negative 3. So p of 1 is going to be 4 plus 1 minus 12 minus 3, and I can see that that's not going to be 0. P of negative 1, what would change is that the cubed term would become negative, the squared term would stay positive, the x term is going to become positive, and the constant stays negative. So it's still negative 7 and positive 13, so that's not 0. P of 3, 3 cubed is 27, and 27 times 4, 20 times 4 is 80, and 7 times 4 is 28, so it's going to be 108. Plus 9 minus 3 times 12, which is 36, and minus 3. Again, those negatives don't balance out those positives to make 0. And p of negative 3. So this is the other thing you need to get good at, is if you've subbed in 3, it's not a lot of extra work to sub in negative 3. So just thinking about what will change. Okay, this will still give a value of 108, but cubing a negative is negative, so it'll be negative 108. Okay, squaring a negative stays positive, so that term's going to be the same. Negative 12 times negative 3 is going to be positive 36, and that's not going to change at all. And again, the positives there definitely don't outweigh the negatives. Okay, so this tells us that there is no factor of the form x minus k, where k is an integer. Okay, so therefore, we're going to assume a factor of the form ax plus b. Okay, so thinking about what we know, the coefficient of x is going to have to be a factor of the coefficient of x cubed. if the brackets are going to expand out to give 4x cubed there. So a has to be a factor of 4, and b is going to have to be a factor of negative 3. Okay. Again, we can worry about the negatives later on. Okay, so really what we know here is we know that a can either be plus or minus 1, plus or minus 2, or plus or minus 4. And we know that b can either be plus or minus 1, plus or minus 3. Okay, so if we think about what that means for the possibilities for b over a, okay, we could have plus or minus 1 over 1, okay, so I'm just going to fix the b value as 1 and run it through the other a options. We could have plus or minus 1 over 2, plus or minus 1 over 4, or we could have plus or minus 3 over 1, plus or minus 3 over 2, plus or minus 3 over 4. Okay, so we rule out the integers that we've already tested. We've already tested plus or minus 1, which is these two options, and we've already tested plus or minus 3, which is these two options. Now, unfortunately, this does still leave us with 8 possibilities. So we have to hope we get lucky early on. Okay, so we've got to start somewhere. So let's try p of 1/2. Okay, so we've got 4 times 1/2 cubed. Let me go back up here, plus 1/2 squared, minus 12 times 1/2, minus 3. Okay, so 1/2 cubed is an 1/8, 4/8 is 1/2. So I'm just going to go straight here, that's 1/2, plus 1/2 squared is 1/4, minus 12 times 1/2 is 6, and minus 3. Okay, I don't need to work out what that is. I know that 1/2 plus 1/4 is 3/4, and negative 6 minus 3 is negative 9, and they're not going to add together to give 0, so it doesn't equal 0. Okay, let's have a look at p of negative 1/2. So let's think about what would be different if all of a sudden this was a negative here. Okay, so the cubed term is going to become negative because negative 1/2 cubed is negative 1/8. Okay, so this is going to be negative 1/2. So I'm just jumping straight from this. I know that term is now going to be negative. Negative 1/2 all squared will still be the same as positive 1/2 all squared, so that's still going to be 1/4. I'm keeping that second term. Now we've got negative times a negative, so this is plus 6, and then we've got minus 3. Okay, let me just get rid of those. Get rid of those negatives there. Sorry. Okay, so again, I'm thinking I've got negative 3.5 and positive 6 1/4, so they don't give 0. All right, let's try p of 1/4. Let's see if we can do a bit in our head here. So we're going to have 4 times 1/4 cubed. Now 1/4 cubed, 4 cubed is 64, so it's 1 on 64. And we've got 4 times that, so it's going to be 4 on 64, which is 1 on 16. Okay, so it's going to be 1/16 plus 1/4 squared, which is also 1/16, minus 12 times 1/4, which is 3, and minus 3. Okay, so not quite, but I'm actually liking the look of these numbers. I think if I change the sign, all of a sudden I'm going to have the negatives in the right places. So if we try p of negative 1/4, the cube term is going to become negative. The squared term will stay positive, so they're cancelling each other out. The x term is now going to become positive because it'll be negative 12 times negative 1/4, so plus 3, and that'll be cancelled out by the negative 3. So this does equal 0. Okay, so if p of negative 1/4 gives 0, that means that 4x plus 1 is a factor. Okay, so remember, the value that you sub in is what you get when you make this equal to 0. So 4x plus 1, when 4x plus 1 equals 0, 4x equals negative 1, x equals negative 1/4. So that's what we want. Okay, so 4x plus 1 is a factor. So we've used the rational root theorem to identify our factor. Now we can do our long division. So we're going to do 4x plus 1. Sorry, I should have written a bit smaller. We've got 4x cubed plus x squared minus 12x minus 3. And we can do our long division. Hopefully we can get through this fairly efficiently. We've been doing a lot of this. What do you multiply 4x by to get 4x cubed? That's x squared. and then we do x squared times 4x plus 1, and write it underneath, so it's 4x cubed plus x squared, and then we subtract. Okay, so we've got this 0x squared happening here, so we do just need to be a bit careful about that. Just persist through it. Okay, I know it's a bit awkward, but we'll go with it. So what do I have to multiply 4x by to get 0x squared? Well, that would be 0x, so there's no x term in the quotient. Multiplying 0x by 4x plus 1, again is 0x squared plus 0x, and subtracting. So we do need to persist through that so we can still work with our negative 12x and our negative 3. And then the question is, what would we multiply 4x by to get negative 12x? That will be negative 3. Multiplying negative 3 by 4x plus 1 is looking good for that 0 remainder. So that confirms that 4x plus 1 is indeed a factor. And so now we know that our polynomial, which was, I'm just going to call it P of x is 4x plus 1 times x squared minus 3. Now the question says, let's just be clear, it says factorize, okay? So that's perfectly fine to stop at that point. You could, if you want to, further factorize the quadratic to be x minus root 3, x plus root 3, using difference of two squares, okay? But that's why you can see, you know, those two linear factors have surds, so that's why we didn't find those using our factor theorem, and therefore the only one we're going to be able to find is the rational one using the rational root theorem. Okay, I'd suggest that you pause the video here and see if you can have a go at example 2 yourself, thinking through the logic of what needs to be done there, and then once you've done that, you can come back and you know, quickly watch through or fast forward to the end of my solution to see whether you've got it right. Okay, so hopefully you've had a go at this and you think you've perhaps got it correct. So let's have a think about using the rational root theorem to factorize, well, just to factorize this, sorry. Okay, so let's try, we wouldn't jump to the rational root theorem straight away. So P of 1 would be 2 minus 1 plus 1 minus 6, which isn't 0. P of negative 1 would be negative 2 minus 1 minus 1 minus 6. So all the terms are negative when we put in a negative. So I think that's pretty much confirms for us that it's not going to be anything negative. P of 2, so I'm looking at factors of 6. Okay, so P of 2, 2 cubed is 8, 2 times 8 is 16, minus 2 squared, which is 4, plus 2 minus 6, so it's plus 18 and minus 10, so it's not 0. P of negative 2, what will change? So we'll have negative 16, we'll still have negative 4, we'll have negative 2 and negative 6. So I think I can pretty much rule out that it's definitely not going to be anything negative, because whenever I sub in a negative value, all 4 terms are going to be negative, so it's not going to equal 0. P of 3, 3 cubed is 27, times 2 is 54, minus 9, plus 3 minus 6. Again, the positive 57 is not outweighed by the negative 15, so not 0. P of negative 3 would be negative 54 minus 9 minus 3 minus 6, so not 0. P of 6, some big numbers here, 6 cubed is 216, times 2 is 432, minus 36, I think nothing's going to balance out that 432, the number's just too big, minus 36 plus 6 minus 6. Okay, so definitely not 0. And then P of negative 6, they'd be all the same values but negative. So also not going to be negative. Oh, sorry, also not going to be 0. Okay, so there's no factor of the form. Okay, so this tells us we have no factor of the form x minus k, where k is an integer. Assume factor of the form ax plus b. Okay, so let's think about what we know about a and b. So a is going to have to be a factor of 2, and b is going to have to be a factor of 6. Okay, so a could be plus or minus 1 or plus or minus 2, so fairly limited for a, which is good. B is a bit less limited, but I think it's still going to work out okay. Could be 1, 2, 3 or 6. Okay, so then let's think about what that means for the options for b over a, which is what we're going to need to substitute in until we find something that gives us 0. So, alright, let's just start by fixing b as 1. So we could have plus or minus 1 over 1 or plus or minus 1 over 2. If we fix b as 2, we could have plus or minus 2 over 1 plus or minus 2 over 2. If we fix b as 3, we could have plus or minus 3 over 1 plus or minus 3 over 2. And if we fix b as 6, we can have plus or minus 6 over 1 plus or minus 6 over 2. Now I know initially that looks like a lot of combinations, but we're just making sure we're being systematic about thinking about all the possibilities, and then let's rule out what we've already tried. So plus or minus 1 over 1, that's a whole number. We've already tried positive 1 and negative 1. 2 over 1 is a whole number. We've already tried positive 2 and negative 2 and found they didn't give us 0. 2 over 2 is 1 as well. 3 over 1 we've tried. 6 over 1 we've tried, and 6 over 2 we've tried. So actually, although there seemed like more options initially, most of them give us integer values which you've already tested. So there's actually only 4 possibilities here. Okay, so let's hope we get lucky early. Let's try p over half. Alright, what's my polynomial? Let me just scroll back up here so I can see it. So we've got 2 times a half cubed. Actually, let's just see if we can do that. So half cubed is an eighth, 2 eighths is a quarter. Minus a half squared, which is a quarter. Plus x, so plus a half. And minus 6. Okay, so a quarter minus a quarter, they make 0. Positive half minus 6 doesn't make 0, so it's not going to be that. Let's think about what will change if we make it negative half. So the cube term will become negative, so it'll be negative a quarter. The squared term will still be negative. The x term will be negative as well. Okay, so again, in this example, when we sub in negative values, we get all terms negative. So we can probably conclude that it's probably going to be 3 on 2. I think negative 3 on 2 would make everything negative, so it won't be 0. So let's just check that 3 on 2 works. So 2 times, so 3 on 2 all cubed is going to be 27 on 8. And multiplying that by 2 is 27 on 4. And then we're going to have minus 3 on 2 squared, so that's minus 9 on 4. And then we're going to have plus 3 on 2 and minus 6. Okay, so let's see what we've got there. 27 on 4 minus 9 on 4 is 18 on 4, which would be 9 on 2. Oops, sorry. And now we've got, so I just added, all I did in that step was add those two things together. We've got 9 on 2 plus 3 on 2, which is 12 on 2. Oops. 12 on 2 minus 6, 12 on 2 is 6, and so that does equal 0. Okay, so that's good news for us. So if that tells us that if p of 3 on 2 equals 0, it's going to be 2x minus 3 is going to give us, when we solve that equal to 0, that will give us x equals 3 on 2. So 2x minus 3 is a factor of our polynomial. So now we simply do our long division. We're going to divide 2x minus 3 into our polynomial, which was 2x cubed minus x squared plus x minus 6. Oops. Alright, what do we multiply 2x by to get 2x cubed? That's x squared. X squared times 2x minus 3 is 2x cubed minus 3x squared. And we can subtract negative x squared minus 3x squared is negative x squared plus 3x squared. And so it's 2x squared. And bringing down our next term, what do we multiply 2x by to get 2x squared? That'll be x. X times 2x minus 3 is 2x squared minus 3x. Subtracting x minus 3x is x plus 3x, so 4x. And minus 6. And finally, what do we have to multiply 2x by to get 4x? That will be 2. And so we get 4x minus 6, and that confirms the factor. Okay, so our polynomial here is equal to 2x minus 3 times x squared plus x plus 2. So this particular quadratic factor, factors of 2 that add up to 1 don't exist. So we could solve this equation equal to 0 and it would have more than one solution. There would be, well, it depends on the discriminant, we need to think, but there's possibly going to be solutions from there, but it doesn't factorize any further than that. Okay. Alright, so just a couple of questions there, questions 7 and 8C for a little bit of rational root theorem practice. It also gives you some good practice of just, good number work, subbing in fractions, and some good revision of your long division as well.